Hey everybody, Mrs. Fry here, and today we're going to talk about our last topic in exponential modeling. So before we do that though, let's review what you've learned so far. Okay, so first off, you hung out with Mr. Covey for a little bit, and he talked about the basic, catch-all exponential model, all right? Exponential. He talked about the fact that typically we start out with some sort of starting amount or initial value that is multiplied by our base, which encompasses either our growth or decay factor, all right? And then we take that to some power x, which is usually our independent, not usually, it is our independent variable, and it pretty much always represents time or the number of times the percent change occurred. And we're definitely going to use this equation today as we look at a specific example of this exponential model as it applies to half-lives. Ooh, that looks funky, and we don't want to mess with that. Okay, but I do also want to point out that you've also hung out with Mrs. Lemke, and she talked about the continuous model, okay? Basically the same setup, okay? We've got a constant initial value, only this time the base is e all the time, okay? And then that means that our growth or decay rate gets pushed up into the exponent, okay? And it hangs out there with time, okay? So, but the basic gist here to understand is that you've got a constant or initial constant times some base to an exponent, and that's our exponential model. Okay, so with that, what we're talking about today is something that harkens back to a time when Mrs. Fry used to teach chemistry, which is the idea of a half-life, okay? So first off, if you don't know what a half-life is, I'm going to use this little picture here just as a visual representation of what we're talking about. So let's just say, for argument's sake, that this is thorium, okay? Which is a slightly radioactive element that undergoes beta decay. And suppose we had, let's just go with 120 grams of it, okay? If you have 120 grams of it, after a certain amount of time, half of it will decay and become non-radioactive, but there'll still be 60 grams remaining that are radioactive. And then if we wait a little bit longer, in fact, that same length of time, we would have 30 grams left that are still radioactive. I believe the length of time that would take for half of it to decrease for thorium is 24 days. Okay? 24 days. All right. And so then that could keep happening. 15 grams. And so there's a couple of vocabulary terms I want to make sure you're aware of. First off, this length of time between our initial amount and it becoming half as radioactive is called a half-life. A half-life is the length of time needed for exactly half of a substance to become neutral, to no longer be radioactive, okay? And so what is happening during that half-life is that literally we are multiplying our amount in half, right? We are taking a rate, like we're decaying by a factor of 50%. So a lot of times people try to make this, really complicated and really confusing by throwing a lot of different variables at people. Well, let's go back to that basic model that Mr. Covey talked about, y equals a times b to the x. And he talked about the fact that b, that base, represents growth, or in this case, I'm going to focus on decay, and it has to do with the percent. Well, if we're losing 50%, right, we're losing a half, not half of a percent, if we're losing half of our whole, well, that's just 1 minus 1/2, which is just a half. All right, so we could really just think about this as y equals a times, and we could just make that base a half all the time. Now here's the deal. Mr. Covey also mentioned that x, time, is the amount of times that the percent is changed, okay? So it gets a little confusing because the half-life is changing, right, depending on the substance. For example, carbon dating is another type of radioactive decay, and that happens over thousands and thousands of years. Okay, so, while on the subject of why are half-lives important, well, we've got carbon dating. We've just got general decay. And also just, anything radioactive. Substances that then become neutral and turn into stable isotopes. That's important, right? That is relevant in terms of how biology occurs and how certain things in nature happen. There are a lot of different places where this shows up. Anyway, point being that time length changes. So how are we going to account for that? Well, basically, we're going to take the time that things have been decaying, and we're going to divide it by our half-life. So half-life. So we're going to take that x value, which is our total time, and we're going to divide it by whatever our specific half-life is. And I'm going to show you what I mean by that. So this equation right here is a little variation on our exponential model, okay? And by the way, I'm also going to post a separate video that really goes into a bit more detail about radioactive half-life, decay, all that good stuff. So if you're like, I don't remember talking about this in chemistry, and you just need a refresher so that you can understand the context of these problems, then I would definitely watch that video. It's like if somebody asked you to do a word problem about baseball, but you don't understand baseball. Kind of makes it hard to understand. Or like a deck of cards. Same deal. So if you need a little more context, I would watch that additional video. Okay. And then, if you wanted to know, here's, the whole gamut of various radioactive decay. There's alpha, beta, and gamma decay, depending on the type of element that is really making your isotope unstable. And so, like I said, carbon is a very classic radioactive decay that's really helps with dating, how old certain things are. And then uranium is a different substance that decays. It takes a lot longer for that to decay. Anyway, let's do an actual problem with some specifics. So suppose a hospital prepares a 100 milligram sample supply of technetium-99, and that has a half-life of 6 hours. So first off, the decay factor, we're not trying to trick you here. Anytime it says half-life, the decay factor is a half. That is what your base is going to equal, right? Remember, we're just using this a times b to the x situation, okay? What's the length of the half-life? So again, we're just establishing some vocabulary. The half-life is 6 hours long, okay? So now we're going to write an equation to represent this problem. And I want you to just think about, you don't know how long. Let's say somebody goes to prepare this sample, these 100 milligrams, and then they go to lunch, but then they get distracted. You don't know how many minutes or hours they're going to be gone. So that time is our x. So we're talking about y equals 100 milligrams times a half. And then our exponent, I'm just going to use my caret just so you know for sure that this is an exponent, is x divided by 6. Okay? And it's x divided by 6 because that's implying the total time divided by the half-life. So now let's do a specific example. Suppose we know that technetium sat maybe at the hospital waiting to be used for 75 hours. So we've got 100 times 1/2 to the 75 over 6. Okay? And so that's quite a few half-lives. Now the easiest way to go about doing this, folks, would be to pull out my calculator and take 100.5 to the 75 over 6. Okay? And just let your calculator tell you that answer. Okay? That's a very, very small amount. I believe this was in milligrams, so we're going to round to 3 decimal places, so 0.017. So y is approximately 0.017 milligrams. For those of you chemistry nuts out there, that's still only 2 significant digits for our 75 hours. So it all checks out. Okay. I'm moving right along here. as I had mentioned to you, carbon-14 is one such element that we use to determine the age of artifacts in what's called carbon dating, and its half-life is much, much longer, 5,730 years. So if we were to write a function for a 24 milligram sample, that's our initial amount, we would say that y equals 24 times, again, we're talking about half-life, so a half of x to the 5,730, x over 5,730. So if we wanted to find the amount after 30 millennia, that's 30,000 years, we would simply plug that in for x, okay? So hopefully you're getting the gist of this idea that we would, plug in our total length of time and divide our half-life by it, because that'll tell us like how many half-lives, okay? But something doesn't always decay in exactly, 4 half-lives or 3 half-lives. Very rarely does it decay super nicely. So that's why we set up our exponent to look like this, okay? And so again, go to my handy dandy calculator, 24.5. And then some of you may need to use parentheses, so I'm just going to show you what that would look like. 30,000 and then 57, 30. All right. Because not all of your calculators may do that. So 0.637 it looks like. Approximately 0.637 milligrams. All right, so hopefully you're feeling pretty good about that, especially if you're just given all that information on the right-hand side and asked to, basically plug and chug, so to speak. All right, at this point, I would like you to take some time to try problems 4 and 5 for us, okay? So you want to read this problem about phosphorus 32, which is involved in plant fertilizer, and this example down here about mercury and how that's used in kidney scans. So see if you can find the answers to those 2 questions, part A, B, and then just problem number 5. All right, and then we'll come back and check your answers, and you'll be good to go. All right, folks, so hopefully for number 4 you got y equals 50 times a half to the power of x over 14.3, and then you got 0.852 milligrams for that phosphorus 32 problem. And then for example number 5, I hope that you had the correct setup of 12 times 1/2 to the 72/64, which leads you to 5.502 milligrams. Now I noticed that all of these problems have the same sort of setup where you put all the numbers in and then you get out an ending amount. I do want to point out that this exact type of equation is what we could use to find a half-life of a substance if we did not already know that the half-life was 72 hours or 84 days. Just by the nature of taking a sample, letting it sit out for a certain amount of time, and then extrapolating that and sort of testing that. So this equation can be used for more than just finding out how much substance you have at the end of a certain amount of time. You can use it to figure out an initial amount, you could use it to figure out the length of a half-life, or the total length that some substance has been sitting out. So just keep in mind that there are a lot of different applications to this, even though we kind of took one main direction for each of these example problems. All right, thank you so much, folks, for listening, and I hope you have a wonderful rest of your day. Okay, bye.